Hello, my name is Scott Grizzard from the University of South Florida. This is Calculus Fall 2020. This is Lecture 9A on minimums and maximums, Fermat stationary point theorem, and the extreme value theorem. As usual, there is chat in Discord, and there is chat in Twitch. If you want to see something totally embarrassing, you can watch my last Twitch stream where I messed up 2 out of 3 of the simple problems from pre-calc because my pre-calc is not all that great. I do calculus. So hopefully now will be much better. So what we're going to talk about tonight is we're going to talk about, first we're going to go over what the big idea is for this module. So there are a couple of it's mostly based on applications, but it's also got a lot of theory in it too. So what we're going to do is we're going to go over that first, and then we'll go over the definitions for max and min, and then what the extreme value theorem says, and then what it means as far as what it implies, and then we'll talk about Fermat's stationary point theorem. Which is very important for what we want to do. And Fermat's theorem has a couple dangers because it's easy to think that it's 2 ways, and it's only 1 way. So we'll talk about that tonight. All right. So let's go ahead and look at what we've got here. So as I said, I want to do an overview first of Module 3, and then I want to talk about mins, maxes on closed intervals, the fact that they always exist, if you've got a closed interval, and then I want to talk if your function is continuous on a closed interval, and then I want to talk about how we can find out where they are, and then sort of the implications of these things. But let's first talk about what the big idea is in Module 3. So there's 3 major ideas, and then there are a bunch of implications. So things like L'Hopital's rule, the formal proof of the whole thing. I did it last time as sort of a thing that's a consequence of linearization, and the intuition is a consequence of linearization. But the full proof you need the mean value theorem for. So we need to talk about the mean value theorem and what it means, right? If I've got, and it's kind of like the intermediate value theorem, only it deals with derivatives instead of just continuous function. Now we've got functions that are differentiable. So like, suppose I've got a 70-mile stretch of toll highway, and the speed limit's 65 over the whole stretch. My car only takes an hour to go from the toll booth at the beginning of the 70-mile stretch to a toll booth in the end. So in other words, I'm a good, I'm a little early. Is a police officer justified in writing me a ticket for 70 miles an hour, even though he never observed me going higher than 75? In other words, was there a time when I had to be going 70? And that's a very intuitive notion, but it's actually something we're going to prove. And that's called the mean value theorem. And then we want to do problems that are like optimization. So these are, very popular in economics, very popular in physics. And what we want to do is this kind of constrained optimization with 2 variables. So we've got some kind of Acme Corporation producing widgets. And those widgets, the quantity of output is like k to the 0.5 or the square root of k times the square root of L. These exponents can be different things. And it doesn't necessarily have to be something multiplied like that, but that tends to be what we see in economics. But I can have other things. And then I've got, some kind of cost, right? So it costs me money to make these widgets, right? I've got to pay my workers, and I've got to pay return on my capital. So if I've got machines, I need to pay the bank a mortgage, right? Because the bank bought these things, and I'm basically renting them from the bank in a sense, except I get to keep them when I'm done. Hopefully they haven't completely depreciated by then in terms of their usefulness. Where R, hopefully they aren't completely worn out by the time I'm done. Where R is rent paid to capital per hour, and W is kind of the hourly wage rate. That's how I think of these. So I want to say if we're producing 50,000 widgets, what's the cheapest way to do it? Okay, so And we're going to talk about that. You kind of make one function, you take the derivative and set it equal to 0. And we're going to start this bit tonight. So getting to this is we're going to start that tonight. Okay? Kind of the theory behind solving those types of problems. And then we've got another one. So given a cost function that's like x to the 1/3 or x to the 0.33 or something like that, plus x squared over 500, right? I mean, this cost function, kind of a laser-guided shotgun, that one, right? Because it's not really that. They're never that clean. But I've got this kind of idea behind a cost function, and then I've got this idea of I've got this kind of shape of the cost function. So something like this would look something like it'd come up like this. Now, cost is always positive when these numbers are positive, but this function is going to look something like this. And it's going to have a bit more of an S to it. Right? So there's some area over which I'm having diminishing marginal cost. Okay, so this is total cost here. That's that C business. But then if I take the derivative of something like this, it looks something like, the derivative looks like this. So here I've got increasing marginal costs. And they're always positive, but, sometimes when I take the marginal cost, it comes up, but then it actually starts to go down. It's always above the axis, but it does something like this. So there's a period, right? They start out really high, right? At the beginning, I have to buy equipment. It takes me, I'm sitting there working myself with 2 other workers or whatever, one other worker. And in order to produce this range here, each one costs more and more to make. But then I come to a point where where my marginal costs are decreasing, right? Where it costs less, right? We're getting good at this. We specialized. I've kind of got like 4 people working now. Some of them are making this part of the widget. Some of them are making this part of the widget. We've got, Adam Smith's old pin factory division of labor, right? So we get better and better and better and better at it as we specialize the tasks. We might get some more machines involved. It might be worth it now to do that. So as we specialize, our marginal costs, our cost at the margin, we still have to buy all the raw materials, but our costs at the margin go down. But then at some point, management, we've suddenly got, while we're making 500,000 widgets, the cost of management, suddenly everybody, all the bureaucrats in HR are setting up their own little fiefdoms. And the cost of producing more and more goes up, right? Because now I've got this giant overhead. We're no longer a nimble little company, right? I've got overhead. I've got compliance costs. I might have 2 or 3 lobbyists in Washington. Those things cost money. At some point, my marginal cost starts going up again. And this is the idea. What can the derivative and what can the second derivative tell us about what's going on in the world? So what's the story that these derivatives are telling us? Right? So what is the story that the derivatives tell us? And this is, I'm using economics things, but this is common in biology has these things. A drug learning curve definitely has these things. We'll do one. And there are other things, right, that all of it, right? Chemistry has this. Reaction rates in physical chemistry look like this, right? They're really fast at the beginning, but then all of a sudden, as the number of free things to react goes down, the reaction rate slows. And there are other things that do this. Okay? So that's kind of the idea. Those are the big ideas. And we actually started this today with the problem set. Okay. So how do we feel about where we're going 1 to 5? Okay. I don't really have a... okay, it's the 5 poll is not working in Discord, so you'll actually have to tell me the 4s and 5s and things like that. Okay, so that's kind of where we're going, and instead of just going the doom, the doom, the doom, the doom, because these are kind of, big topics, we're going to kind of mix them up together a little bit, all right? Because we want to gain intuition on these two fairly quickly, because the intuition is really important, especially for this last bit. But we're going to start here today. We're going to start here today by talking about mins and maxes and Bolonzo's extreme. It's actually Bolonzo Firestrass. I should have put his name up there too. The extreme value theorem and Fermat's stationary point theorem. All right. Well, let's talk about the absolute most intuitive definition of all time. Okay. Minimums and maximums. So what does it mean to have a function to have a minimum and maximum? All right, so what we're going to say is this. All right, and this is going to be a common thing. I'm going to say D a lot, right? A lot of times it's not going to mean anything, but it's going to start having meaning. So I'm just going to start doing it, right? So let D be an interval. All right, and F be defined on D. And I don't care if it's an open interval or a closed interval or what it is. I just care that it's it's there. Oops, I didn't want to do that. I want this to go back to purple. All right. So this is a definition. Let's see. All right, and then let A in D. Okay. So A is just some X value in D. All right. So what I want to say is this: I want to define what it means to have a maximum and what it means to have a minimum. All right. So this is very intuitive, right? If I've got a function here, and let's call this A, what does it mean to be the global maximum? It's the biggest thing around, right? So globally, I'm going to say F has a global max and I'm going to say global max over D, right? So it's the global maximum over this interval at A, which is X equals A, at the X value A, if, well, let's see, it's bigger than everything else. F of A is greater than or equal to if for every X in D, F of A is greater than or equal to F of X. Okay? And this is the thing for global max. So what is it? It's the biggest thing around. Right? It's the biggest thing everywhere. Right? It's the world's, tallest dude. Not just in America, I mean everywhere. 1 to 5, how do we feel about that definition? All right. If f of a is greater than or equal to f of everything else, I call it a global max. Now, notice there's a little bit of trick. Okay, there's a little bit of a trick, and that is that if I have a flat line, everything's a global max, right? So if f of x equals 4, right, then 4 is the global max, and it exists everywhere. Okay? Now, it should be noted that the y value is the global max, right? So this should really read f has a global max and then I want to say more than this. I want to say this is first part. The second part is that f of a is the global max. Over D. If for all x and D, f of a is greater than f of x. So there's this annoying little difference between has and is. Okay? So that's just a little thing you just need to keep out. Okay? Is means the y value. And that's just one of those annoying things that you just have to watch out for. And normally I wouldn't even mention it, but, you know, I don't want you to go, oh, look, well, no. So it should be noted that a global max is a y concept. Okay? So here is f of a, and this is the max. Okay, there's a small subtle distinction there. I just want to make sure you don't step in it. All right, in the same vein, what do you think it means for f to be a global min? F of a to be a global min? Let's see if I can put this thing together. F has a global min over D, or f of a is a global min over D if for all x in D f of x is greater than, so I want to say f of a is less than, f of a is less than or equal to f of x. And the picture, of course, looks like this. Is anyone absolutely totally shocked by that picture? All right. Oops. All right. So 1 to 5, how do we feel about those definitions? Okay. And do you really need examples? I'll do a few, but I'll do a few when we're actually looking for them. Okay. So the problem we have is that, let's say we have f of x equals x squared. And let's say f of x equals x squared over the interval over d equals, let's do -2, -1. All right? So, do we have a global max? And do we have a global min? All right, so let's look at this. F of x equals x squared, right? So what I'm going to have here, and my interval is -2 and -1. So I'm going to make this 1, this -1, this point here, so that's that point. This point here is -2. I don't need this huge tail on it because it's a positive. It's always positive. But I need more room because I got to go to 4 here. So here's 1, here's 2, here's 3, there's 4. I didn't quite make it large enough, and it's going to be in the way, isn't it? Let's see. Come here. All right. So here's my function. Oops. Right. Now I've got -2 maps to +4. -1 maps to +1. 1/2 maps to 1/4. 0 maps to 0. And 1 maps to 1. But I don't actually have this because it's an open circle. Okay? All right, so my y values, my range, or my image of D, is the set, so this would be f of, the notation for this is f of D, right? So my f of D is the open set. Now here I'm going to get to 4, but that's actually at the height, right? So this is where I actually hit. Right? These are my y values. So I'm going to wind up with the y values of 0, 4. Now, does this function have a max? Well, not really, right? Okay, the global min is easily. The global min here is y equals 0. But the global max does not exist. All right, so how do we feel about that 1 to 5? That this function has a min in its y values, but it doesn't have a maximum. Okay. 1 to 5, how do we feel about that? Oh, the microphone's way over here. No wonder you can't hear me. Okay. So here what I've got, right, the global max doesn't exist. How do I know? Well, suppose it did. Suppose it was V. Okay? All right, so wherever V is, I don't care. But then, if I do 4, if I do half the distance, where is V plus half the distance to 4? Right? Suppose it was. Well, then I can always find something bigger, right? If I have, suppose you told me it was 3, well, I'd say, okay, well, 3 plus 4 minus 3 over 2, otherwise known as 3.5, is closer. Oh, you say, okay, 3.5. Well, 3.75 is closer to 4. All right, you say 3.9. I say, 3.95. Right? So, if it did have a max, I could always find something bigger, which contradicts the thing of a max. Okay? How do we feel about that little side statement, 1 to 5? That I could always find, if I did have a max, if you said I had a max, I could always find something that's a little bit closer up here. Okay? Okay. All right. So when do I have them? Well, sometimes I have them when I don't, but other times, I there are times that I get them guaranteed, and this is called the Bolonzo's, sometimes called Bolonzo Firestrass, but this is a big named theorem. Okay, so this is a big named theorem. And when I say big name theorem, the name should be going in your book, and you should be printing it off and pasting it on the wall and making sure you know it. All right. This is Bolonzo Firestrass. I'm sorry, Bolzano, not Bolonzo. Bolzano Firestrass. Extreme value theorem. Okay. The extreme value theorem is what the book calls it. I'm putting in the names. Fine, you don't need to remember them. Bolzano. Is it B-O or B-A? Nope, B-O. That guy. Okay. There's actually something else called the Bolonzo Firestrass theorem, by the way, which is a generalization of this. But this is what it says. It says, so it says the following: let D be an interval. And let F be defined on D and give values back to R. Okay? It says the following: if D is a closed interval, okay? That's the key. Then there exists A and D so that F of A is the global max of F on D. And the other thing that says, and there exists B in D so that, if D is a closed interval, I'm sorry, and if F is continuous on D. I'm always forgetting that one. If D is a closed interval, and if F is continuous on D, then, there we go. Sorry about that. Oops. There we go. Then there exists a B so that F of B is the global min of F on D. All right. So 1 to 5, how do we feel about that statement? So the intuition is rather, here's the picture that I always draw, which I didn't draw, and because I didn't draw it, I didn't remember the second thing until later. Right? I've got this idea here where I've got a closed interval. Right? I'll call this right here D is closed, is a closed interval. By the way, F can be defined more, but I actually don't care, right? I'm talking about this particular closed interval. Now, somewhere there is an A, so that F of A is the global max. There it is. And somewhere there is a B, so that F of B is the global min. And it can be at the endpoints, and that's the point. Right, so here, on this particular D closed, right? Here's F of B, and here is F of A. But it doesn't have to be, right? I can have, right here, here's the max, there's A, that's the max, and the min is interior. Okay. So how do we feel about that 1 to 5? I've got this definition here. And I've just got, I've got this theorem, and all it says is that, it says that I'm going to reach, so in other words, if F is continuous and D closed, then F attains both a global max and global min. All right. Now, okay. So if we look at the same function before, right, we had f of x equals x squared, but we're going to let d equal the closed interval -2, 1. Right, so now I'm going to shut down that little thingamajigger that I had going on there. Going on at 4. So I'm no longer going to allow us to play that game. Oh, but I could get closer to 4. Well, now you can't, because now I've got a point here that's a hard end. All right, so it's the same setup as before, but now I've got a hard endpoint. I've got 2 hard endpoints, as a matter of fact. So I've got a global min. That one's 0. Global min is 0. And my global max equals 4. How do we feel about that 1 to 5? Okay. Now, there's a slight aside, and we're not going to prove this theorem, by the way. This theorem is the goal of analysis 1, is to get to this theorem and the intermediate value theorem. That's kind of the goal of a 4,000 level class, which is designed to torture you if you're a math major. So that's sort of the goal of that class. But so obviously we're not going to prove it here. But there's an implication here that's rather interesting as an aside. Okay. Okay, so let's recall the image of a function of a set is the y values reached through f through set D is the y values reached through f from D. Okay, so in other words, f of D equals f of x such that x is in D. Right? So it's kind of like the range, only I want to have a small domain. So if I think about this as restricted to D, right? If I think about this as I restricted the function to D, I could think of this as the range. I'll put F to find out D here because I'll make that part of the notes. Okay, so I want to just think about this as the kind of range, but if I restricted my set, right? So here, F of D equals 0, 4. Okay? So, combined with the intermediate value theorem, so the intermediate value theorem plus the extreme value theorem together imply that the image through a continuous function I should say the image of a closed interval through a continuous function is a closed interval. In other words, f of D is a closed interval if f is continuous and D is a closed interval. Okay. And that's a nice little aside, just to kind of keep in your back of your mind, that I can think of it this way. And that's actually a good way to think about it if you want to solve certain types of problems. So 1 to 5, how do we think about that? It basically says that if I've got a closed interval and a continuous function, I hit everything in between. Okay, I did not know that. Someone has just pointed out that the chat channel in Discord was locked. Oops, sorry. I did not know that. It didn't have the little lock button. It's one of those days. Okay. All right, so now I want to go about finding these things. But in order to do that, I'm going to have to define what I mean by locals. Okay? So I need a couple more definitions before I could find it. So I'm going to need two more, really one more definition. And a very powerful theorem. Okay. So let's get some more definitions down. So the first of these definitions they're both the same, right? So the same thing, same setup. Let D be an interval, a point in D, and F defined on D. Okay. F of A is a local min if for all x near A, f of local min, f of A is less than or equal to f of x. F of A is a local max if for all x near A, f of A is, this is a shocker, greater than or equal to f of x. All right, so the idea here is I could have a function that looks like x cubed minus x. So if you pull up the function x cubed minus x, this is a nice one. Let's see here. I want a new. I want to save that for later. So if I've got x cubed, not squared, cubed minus x. Let's do x squared. Maybe that'll be a nice. Nope, x was better. So if I have x cubed minus x, it looks like this. Let's see. Doop, doop, doop. Let's see. Here's the example. This is x cubed minus x. Nicely. I've said that 6 times now. Maybe not. Maybe I should go count. Okay, so here's what this function here looks like. Let's get rid of some of this stuff. Let's make it a little bit bigger. And let's set it as the background. So this right here, let's see, label this f of x equals x cubed minus x. So this is a nice function here, right? So I've got kind of this idea that I don't really have a global min, right? I would if I restricted my domain to something, just on the side. But I have this idea that right here and right here, right, I've got something that's it's not the biggest guy in the world, but he's the biggest guy in the neighborhood, right? And you have to say the neighborhood, right? If I restrict my X to right here, he's biggest, right? So here I've got a local a local max, right? Biggest guy in the neighborhood. And here I've got a local min. All right, that's not working. Right? So it's not the biggest guy in town, but it's the biggest guy in the neighborhood. How do we feel about that 1 to 5? Sort of an intuitive notion. Okay. All right. Now, there is a thing here. Can local... So this is a total aside. Okay? And I don't want to do this, but different books state whether or not local maxes or min's going to carry them points. I say yes. Some books, this one says no. It's one of those things that, people without anything better to do argue about. Different books say different things. I'm going to say yes, and I'm just not going to care. And if for some reason the test goes no, I'm going to say not in my class. And I'll mark it, and I'll just mark it right, because that is just one of these little piddly little things that people without anything better to do like to argue about. Okay, but here's what we have. Now, notice what's going on here. If I pull out a ruler, what's the slope of the tangent line there at the max? It's 0. And here, what's the slope of the tangent line here? 0. Okay. All right. Notice that the slopes of the tangent line are 0. That's going to give us our big theorem that we're going to use to hunt these suckers down. Okay. So here's the big theorem. It's called Fermat's stationary point theorem. All right, and it's our biggie. And let A and A. Let's let the point. Let A and D. All right. If F is differentiable at A and F prime of A equals 0. Nope. If F is differentiable at A and if F has a local min or local max at A, then F prime of A equals 0. Now, there's another way to write this. If f has a local min or max, at x equals a, then either f prime of a equals 0 or f is not differentiable at a. Okay, so there are two kinds of forms of this, and they're logically equivalent. Okay, but this is the statement of the theorem. This is kind of a logical equivalence that's more useful working out. Okay, so 1 to 5, how do we feel about the statement of this theorem and what it means? All right. What this means is that if I can go hunting for local mins and local maxes. Okay. So note, by the way, that the converse is not true. F prime of x can be 0 and nothing particular happen, and but f not have a min or a max. But f not have a min nor max. And the perfect example of this is, think f of x equals x cubed. Okay, so f of x equals x cubed is the perfect example of this, right? If f of x equals x cubed, this whole thing should be in red because it's the biggest mistake people make, right? Here's f of x equals x cubed. Right there, f prime of x equals 0, but neither min nor max. And I want this whole bloody thing in red because this is kind of a trap. All right, so the converse isn't true. But I can cut down on the places I have to check. Okay. But I can use this to cut down on the places I need to check. Okay, so let's do this. Let's go back to our friend here, but let's do, so 1 to 5, how do we feel about that little fact? That it's not something that's going to give me, peace, joy, and happiness for the rest of my life if I, under all circumstances, right? It can have places where I'm just going to wind up with things that aren't really hunky-dory. 1 to 5, how do we feel about that? Okay. All right, so let's go back to something. Let me get something with nice roots here. So let's see. If I do 3, that'll work. All right, so let's look at a modification of our thing. So let's consider the function so find the global min. So let's do an example. Find the global min of f of x and global max of f of x equals x cubed minus 3x. All right. So this is a modification on the theme we had before. And I chose this because it's going to have nice roots when I take the derivative. Okay. And I'm going to do it on the interval. Let's do the interval -3, 1.5. Okay. All right. Yeah. Okay. First note. Phi EVT both exist. Okay, so now I'm going to hunt for them. Step 1. Okay, take the derivative. What I'm going to do is I'm going to make a list of places to check. All right, so our goal is to make a list of places to check. Okay, so step 1, I'm just going to add the endpoints to my list. So step 1, add endpoints to my list. Let's just do that first. Step 2, take the derivative. Okay, so let's take the derivative of this, and I wind up here. So what are my endpoints? So my list, my running list looks like here. So I'm going to have a list here, list of x's to check. Okay, the first are the endpoints, -3 and 1.5. They go on my list before I do anything else. Now I'm going to take the derivative, and I'm going to get f prime of x equals 3x squared minus 3. Yep. And now what I'm going to do is I'm going to set the derivative equal to 0. Okay. So I'm going to set this equal to 0, and I get 0 equals 3x squared minus 3. The 3 factors out nicely. And I get 3x squared minus 1, and that becomes 3, and that's a difference of squares, and I like that. And I get 3x plus 1 times x minus 1. So how do we feel about our little factoring? So x equals -1 and x equals 1. 1 to 5, the little factoring there. All right, add my zeros to the list. Step 5. Oh, step 4. So I need to add my zeros to the list. So right now, my zero, I have -3, 1.5. Those were the endpoints. I'm going to add -1, and I'm going to add 1. Okay, step 5. Add any points where the derivative does not exist. Because if I had something like absolute value, right? If I had something like absolute value, there'd be a point where the derivative didn't exist. And it could be a min. In fact, for absolute value of x, it is. Add the zeros to my list, I should say, as long as they are in my interval. Okay, add the places where f prime of x does not exist. and again, within my interval. Right? If I had a 0 that was like, let's say -6 was a 0, I wouldn't care because it's outside. Okay? Here, it's a polynomial. It's differentiable everywhere. There's no places for step 5. Step 6. Plug my values, my x values, my x list, back into the original equation. All right. Okay, so this is my step 6. Back to the original. All right, so I'm just going to check them off. So I'm going to do f of -3 equals. Now, don't do f prime. I want f. -3. As a matter of fact, I'm going to write f right here so I don't look back and I don't go, oh, f prime of x. No, I want f. Okay? Come on. It won't go up. There it goes. All right, so I want f. So I'm going to f of this is -3 cubed minus 3 times -3. Okay, well, -3 cubed, this is -3 squared. So, you know what? I'm just going to, like, sit here and go, okay, that's -3 times the quantity -3 squared, because that's just making me mad, minus plus -3 squared. Okay, so it's not going to help me at all. Never mind. Okay, so -3 cubed. Well, let's see. It's -3 times -3. That's going to give me +9. And the next -3 is going to be -27. Plus regular old 9, because I got added there. And that is going to be what? I'm horrible at math today, so, you ought to tell me. -18, if I'm not mistaken. All right. F of 1.5 equals, well, let's see. I had to pick 1.5 cubed. I don't trust myself today to do things like that. All right. So this is going to be 1.5 cubed minus, let's see, this is positive. So here I'm going to have -3 times 1.5. Okay. And again, I don't trust myself today. So 1.5 cubed is 3.7, 3.375 minus 3 times 1.5. That one I should be able to do in my head. I didn't say I would. I didn't say I should be able to do it. I'm not sure I can. That one's 4.5. Okay. Minus 4.5. And I add those two numbers together. And I wind up with 3.375 minus that. And I wind up with... That's not right. I put a 1 in front. That's still not right. $1.5. There we go. Equals negative 1.125. All right, now I'm going to go through the list again. I've got f of -1. Oh, thank goodness, something easy to compute. Okay, so my original equation is here. So this is going to be -1 minus minus, which is going to be a plus of 3. And that one I can do in my head, even today. And f of 1 equals, okay, so 1 cubed 1 minus, okay, so 1, I'm going to throw it in here. It's going to be a minus 3, and that one's going to equal negative 2. Step 7. Pick the y's that are biggest and pick the y's that are smallest. Okay? That one's hard. So 1 to 5, how do we feel? Wait, did I mess something up? Nope, I didn't. Okay. Well, I didn't mess something up that you caught. Right? Okay, so the biggest and the smallest. Well, let's see. There's the biggest. And there's the smallest. Okay? Step 8. Write what you found. Now, again, I'm going to encourage you to say what you did, right? So F has a global max of 2 at x equals negative 1. F has a global min of negative 18 at x equals negative 3. Okay? Actually, I only need to write the y values if it asks me for the min and the max. Okay? And the point of this is I've actually solved for the interval. Right, I've actually solved for the image. The image would be negative 18, 2, closed. But that's just an aside. Okay, so 1 to 5, how do we feel about this problem? These are kind of the steps, and you can write your own. And then if we look at this, if I give you the graph, what'd I say? Negative 3? That's going to be way off the graph. Okay, well. Negative 3 was a big number in terms of this problem. There we go. So we want this to shrink. We want this to come over. We want this to come up. Negative 3. There we go. So let's do this. So if we look at this graph, note that it's not drawn to scale. I'm sorry, the scale on one axis is different than the scale on the other. I get something that looks like this. You can't see it yet. So I wind up with something that looks like this, and sure enough, there they are. So here was my hard interval. My hard interval was negative 3 to 1.5. So my hard intervals for my x values were here and here. So here were my x's. And then I've got this max of 2. So here's the global max. And then here is the global min. And this is a local. And this one's a local only, or local max. Okay, so that's basically what happened. How do we feel about that? Okay, well, because this book is annoying in some senses, there's actually a word for this. So the book is going to define this as a word. So this two steps, basically they want to combine two steps and give it a name. And these are called check for critical values. Okay. So there's this weird definition here, which is a minor definition, right? This is a minor definition. It doesn't quite deserve a capital D. All right, so let f defined on interval D f A is in D. A is a critical number for f on D if, this is kind of in parentheses, right? For f on D. A is a critical number if f prime of A equals 0 or f prime of A does not exist. Okay, so 1 to 5, how do we feel about that little definition? It's a little minor definition. It's one of those definitions that people that have nothing better to do love to state. It's a critical number. Who cares? It's a place where the derivative is 0 or doesn't exist. Why do we need a name for that? But we do. So we have one. And you'll see that in WebAssign, it's going to ask you that all the time. Find the critical numbers. What they mean is find the places you have to check to look for mins and maxes. Okay? So 1 to 5, how do we feel about that? Okay. Well, let's do one last thing. Let's just prove Fermat's theorem. It's got a nice little beautiful proof. And it's worth doing because it's nice to kind of look at it. So let's do a proof of Fermat's theorem. Okay, it's a nice little proof. All right, so what I'm going to do, my strategy is going to be this. I want to show the following. I want to show if f is differentiable at A, and f prime of A and if f has a min or max, local min or max, min or max at A, then f prime of A equals 0. All right, and here's my strategy. My strategy is going to be break it into the two cases. Max or min, and show f prime right of A equals 0, and is either greater than or equal to or less than or equal to 0, and f prime minus of A is either greater than or equal to, or I should say less than or equal to, because depending on whether or not you pick a min or a max, 0. And then I use the fact that f of A exists to get that it's, and then use the fact that f prime plus of A equals f prime minus of A. So basically I wind up with 0 is less than or equal to f prime of a is less than or equal to 0. So it's one of these proofs that's kind of neat, because what you're doing is you've got 0 on one side, 0 on the other, and you kind of just do it. And it looks pretty nice. So I'm going to do part of it. Let's just do part of it. We don't have to do both sides. And the other side's analogous. So case 1, let f have a local max at x equal a. All right, so I've got f prime plus of x equals f of x minus f of a all over x minus a. All right, with a limit sign here. And this should be a, not x. Okay, so I've got this idea that I let x just run over to a plus, and I'll have a right-handed limit. Okay. Interesting. All right, well, let's do that. Well, notice since f of x is less than or equal to f of a, since I have a min, the top is less than or equal to 0. Now, since I'm coming from the right, so now here's a, and I'm doing the limit as x goes to a plus. That means x is over here. So since x is greater than a, the bottom is positive. So that means the whole thing is less than or equal to 0. Now let's do the same argument on the other side. F prime minus of a equals the limit as x goes to a from the left of f of x minus f of a all over x minus a. Well, the top is negative again. But this time, x is coming from the other side, isn't it? Right, here's a minus and here's a plus. So this time, the bottom is negative. So the top over the bottom is greater than or equal to 0. Right, so I've got negative over negative. One to 5, how do we feel about that little bit? And remember that both of these equal f of a. So what I've got is this thing here. Right? Here is 0. Zero is less than or equal to f prime negative of a, which equals f prime of a because f prime of a exists, which equals f prime plus of a, which is less than or equal to 0. So 0 is less than or equal to f prime of a, which is less than or equal to 0, meaning f prime of a equals 0. Yeah, a little slick, isn't it? Right? I took this 0 when I started here, and then I just stuck the other there, and that's equal to f prime of a, since f prime of a exists, right? That means the derivative from the left equals the derivative from the right is less than 0. So I wind up with that. Case 2 is analogous. And this is what happens when people run over time, right? You're wondering where all those exercises in the book come from. It comes from the fact that there are things we wanted to do for examples, and then we ran out of time, so we said, oh, I'll just do this at home. All right? Case 2 is left as an exercise for the reader. All right. It's the same thing, right? You do local min, local max, that sort of thing. All right. Are there any questions? Okay, so what we did today was we went over kind of where we were going with this, and then we went over a couple of things. We went over min-maxes, we went over Fermat's stationary point theorem, we went over the extreme value theorem, right? And then we talked about how to solve these problems where I want to look for a max and a min on some interval. And that's going to be key for when we do optimization problems, right? So that's kind of the second half to an optimization problem. You know, you find the things, you check the endpoints, those sorts of things, all right? Next time, what we're going to get into is sort of the beginning of this curvature stuff. Next time we're going to get into the mean value theorem. And then we're going to get into this curvature stuff. And the mean value theorem actually has a whole bunch of implications. So we care about those. And we care about those implications, not just more than the mean value theorem, but we do care about them because it's one of these things that we pick up and we use to do stuff, and we do Rolle's theorem, and they've got nice proofs, and we'll also do more proofs by contradiction. So you kind of got your first kind of little proof by contradiction here today. When I talked about the fact that this thing can't have not there. When I did this is a little mini proof by contradiction. And we'll do some bigger ones later, because Rolle's theorem, the proof is by contradiction, and it's very nice. Okay, Rolle's theorem, I don't know how you say his name. All right, are there any other questions, comments, issues, suggestions, thoughts? Okay, well, that's it for me today. I got to go fix what happened to the last exercises, and I will see you all on Wednesday or Thursday.